Okay, thank you for your attention, and it's late afternoon. So what I'm going to present is my PhD students' work related to early ejection simulation for plastic part processing. So just to mention that this work is developed by my student Junyu, and he cannot make it, busy for the oral defense, so I'm just coming here quickly to cover on behalf of him. So most of us are pretty familiar with the, why the screen seems to cover a little bit. Okay.
It's okay.
Just a quick thing. So molding is a complicated process. And we know that the material melts and then inject into the cavity and take a thermal cooling process, and then after that is solidified, eject out. So the question here we have is that how fast you want to eject out. So especially for a large piece of plastic, if you wait for the full solidification, full cooling into a full solid, it's too long. It will lose money. And I know that in the plastic industry, the cycle time is so short. It's talk about less than 1 minute for one sort, and then you quickly have another one. And the profitability comes from the productivity. And every cycle, if you can save time, you will make money. And plastic really make, we are talking not 1,000, we are talking about 100,000. That is the number of production, right? You make money out of that. So saving the cycle time is critical for making money. And we have this general idea that what happens if you inject into it and then you now cool 100% with the solidification. How about the outer layer is solidified, inner side still molten, and then you eject earlier. But that is something you think about. If the thickness of the wall of the plastic is very relatively thick, then you really have a semi-solidified and ejected out. And then you have side effect that is cooling might be caused deformation. Right? And we all know that this is a critical thing. So what we are proposing, we use computer solutions to simulate the state of the molding and eject the plastic part earlier. That means we accurately predict the deformation, satisfy the quality requirement, and from there you save the cycle time. So that is the idea behind it. So with that, the current research is talk about, there are some good work. Actually, there are some commercial software, Moodflow, doing the simulation for molding process. It's really advanced, can simulate different types of material, different properties, and the cooling stage, timing, and the thermal distribution, and the material state, and so on. It gives you reasonable good kind of simulation. The trouble is that they never tell you when to eject. They only give you the simulation that when the full solidification will be done. And then usually the company set up their process by using conservative approach, basically make sure you have long enough time to cool off. And then we start to think about if you really want to improve the process, compress the cycle, I can semi-finish eject, but I know that the material is still hot and the inner side is still liquid or semi-liquid, and then you put into the air, let the air cooling happening, and then you can save the cycle time. And we have to predict that with the finite element analysis. And then you can imagine that is an advanced topic because material is transitioning from the molten liquid to the solid. And then you are halfway predicting that the solidified layer, how strong it is, whether it's good enough to stand the ejecting force. And then you predict how much deformation. And then satisfy the quality requirement for deformation. And then you see, okay, I give you the guideline, how many seconds you will be ejecting. And then from there, you really make the quality. Of course, you have the manual trial, we call it trial of error, you still save a lot of time. Otherwise, you are testing out the quality and having too much trouble for satisfying the quality. So we have that kind of motivation, we start to use some software. One software is MoldFlow, and one software is ANSYS. And MoldFlow, we import the intermediate stage of MoldFlow data and pump it into ANSYS. And use ANSYS capability to predict the solidification process with built-in residue stress. And then we predict the cooling process to look at the both stages, we call the ejecting stage and the cooling stage in air, so that we can predict the total deformation, and in order to make sure the deformation not overrun the quality requirement. So we do need a lot of input, such as process setting, material data, mold configuration. We also need to have the output, which is expecting the residue stress, pressure, velocity, and temperature at different times of the molding process. And then from there, we monitor very accurately to simulate the stage. So it's the way we do that. If you look at the research tasks, two things, just I really emphasize. One is air cooling shrinkage, one is a mold design and better support the partial solidification. So with that, I just give you an idea how the time will be spreaded. This is a cycle, and the filling time is so much, packing, and then in-mold cooling, and then ejecting, air cooling. And what we want to shorten significantly is this in-mold cooling time. And by the way, in-mold cooling costs a lot of energy because water cooling takes time and thermal dissipation happening. And if you can save it, it will be a good thing. So the input we have is plastic CAD part, and then we make it a mold part. And from the mold part, mold model, and we run the mold flow simulation, and then extract the data from the mold flow and then pump it into ANSYS. And the ANSYS will be doing the simulation for the how much the deformation will be. And then we have the final suggestions for the quality issue. Generally, those are the sample data we interpreted from the mold flow result. And what you will have from the mold flow is that you have the exact timing. At that time, what is the position of the parts, what is the residue stress, and the mesh information. And then in the mold flow, we also extract data such as temperature distribution. And then from there, we go to ANSYS domain, and then we do the thermomechanical couple field simulation. That is one of the software that they have for ANSYS. And the goal, of course, to predict the acceptable quality, and then we really find out the final dimension variation. And the advantage will be increasing the, actually, wait a second. We are trying to address the issues is increase the cooling time and also try to simulate the design changes and what is the effect. It has many different kind of advantages, but these are the two issues we can address. Reduce the cooling time and address the the design changes so that you can predict the quality. All right, let's look at what we have the typical component. This is something, it's non-trivial. I'm saying this real industrial parts. We work with a local company in Canada, and this is, you look at the ribs and so on, you will see that it's not a simple part. Right? And then from there, we have to model them into the mold, and we have to create the mold model, including the cooling channels, including the thermal dissipation. So this is the full mold, complete digital model. After that, you run the simulation from the mold flow. You see the basically the thermal distribution, temperature, and the state distribution. You will capture the data 100%, and then you will pump the information to the ANSYS. And the ANSYS is probably, this is the temperature distribution. And by the way, mood flow can give you temperature distribution, stress distribution, so, and also the physical properties of the material. You pump into ANSYS. And this is the integrated after the mood flow pump the data to the ANSYS. You see the variation, and you see how much the difference. This is we call it shrinkage rate, and based on this, see how the things change, the dimension change. By the way, when we talk about the deformation, it's not a 2-dimensional, it's a 3-dimensional, because this is a 3D part. The rib strength will be not the same in different directions, in different locations. This is a spatial thing, right? You know, for example, the corner probably have less deformation, but the inner part and also the weaker part might be here. Without the ribs will be deformed a lot, but here you have a lot of ribs will be perfectly fine. So you have to know what is the distribution, and with that we will be able to predict the amount of deformation with our proposed approach. And you can see it takes a reasonable amount of time, iteration, and so on. Now, what is the conclusion and the future work we can see? First, we are able to integrate the data from a mode flow to the ANSYS. We can go through the forward linking and predicting the deformation for both states, for the early ejection and also cooling, air cooling. We can do that. So far, you look at the literature, very few people do that, so much advanced simulation. We achieved that. But what we see is we want to do faster, more robust simulation, automated, so that I can provide intelligent advice to new product molding process, advice to the company, say, look, initial setting should be like this. In such a way, they can reduce the time in the trial of error for the setup of the molding process, and typically it takes 2 or 3 weeks in order to make a stable production setup. And if I can cut that time, say, think about the benefit, cutting the setup time from 3 weeks to, let's say, 2 or 3 days, because we give them the input, we give them the simulation result. And think about it, the cycle time for, say, 50,000 kind of a part. If each of them I can reduce 1/3 of their cooling time, then do you think there is a benefit for the profitability for the company? So that is what I want to share with you guys, what we are trying to do. And I'll open the floor, of course, when the time is possible, we can discuss about it. Yes. Thank you for your attention.
Thank you.